NVIDIA built an AI to dream the road ahead. It renders the next few seconds of driving as video, so a self-driving car can be tested against a blizzard, or a kid darting out, all in simulation.
A driving simulator that hallucinates the future. Fine, what's the twist?
They took the thing they built to paint the world, and it turned out to be good enough to drive the car. Same model, and it outdrove a dedicated self-driving system 5 times its size.
So the renderer became the driver. The thing imagining the world understood it well enough to act in it.
And that's the whole week. A few weeks ago we did Jan LeCun's bet, don't predict pixels, predict the idea. Well, this week the entire field went all in on world models. AIs that carry a model of how the world works, and they cannot agree on what one even is. Camps. One says render the future in pixels. One says no, imagine it in your head, in the abstract, the way LeCun wants. One says you don't need a world model at all, just scale. And one keeps asking, can we even tell a dreamed world from a real one?
A whole field arguing about its own holy grail. Good. Start with the dreamers, the ones rendering pixels.
NVIDIA. Of course it's NVIDIA. New here? This is Breach Protocol. We crack open the week's AI research and tell you what's actually inside. The result, not the press release.
I'm Vestra. I chase the mechanism, how a thing works, and whether it survives a hard look. Luna brings the pattern across papers. I check whether it holds.
And I'm Luna. Today is one idea seen from every angle, the world model. The dream of an AI that doesn't just react to the world, but carries a working model of how it behaves. Everyone's chasing it. Nobody agrees how.
So let's let them fight. The pixel camp goes first.
So the problem OmniDreams is solving. Before you trust a self-driving car, you have to test it against the rare, dangerous stuff. A mattress falling off a truck. A kid in the road. You can't safely collect that on real streets.
So you simulate, and the standard way is reconstruction. Scan a real scene, re-render it photorealistically.
Right, and that's the catch they go after. A reconstruction is anchored to exactly where the camera was. The moment your car steers somewhere the original drive didn't go, the picture smears. It can't show you a road you never drove.
Whereas a generative model has watched millions of hours of driving, so it has a prior for what any road looks like.
That's the bet. It generates the next frames of video as the car drives. And it's closed loop. The car steers, that changes what happens next. New view comes back. A live feedback loop, not a replay. And it runs faster than real time on one of their big chips.
Now the part you teased, the renderer that drives.
They took the same model and fine-tuned it into the driver itself. And it beat a dedicated self-driving system about 5 times its size. Fewer collisions.
That's the genuinely interesting result, and I want to be precise about why it matters. If the thing that renders the next frame can also drive better than a purpose-built driver, then the act of predicting the world and the act of acting in it are using the same internal model. The renderer wasn't just decorating pixels. It understood the scene well enough to control the car.
Imagine the world well enough and driving falls out for free.
Cautiously. They call it preliminary, and the honest cost is enormous. The 4-camera real-time version needs a 16 GPU cabinet. This is a server room dreaming a road, not something in the car yet.
And it's pure pixel camp. It predicts the actual video of the future, which is exactly what LeCun says is wasteful.
Which is the fight we're about to have. Hold that, because the next paper takes the opposite bet and claims it's both cheaper and better.
So here's the opposite bet. The task is the same kind of thing. Watch part of a video, predict what happens next. The pixel camp would render the future frames, the text camp would describe them in words.
And both have a problem. Rendering pixels is expensive, describing in words is lossy. The arm swings throws away all the geometry.
Right. So this paper does a third thing. It lets the model imagine the next moment in its own head, in latent space. Not pixels, not words. A few internal vectors that stand in for the imagined future, fed straight back into its own reasoning.
So it pictures the future as a thought, not a picture. And this is exactly the JPA move. Predict in an abstract representation, never reconstruct the image.
It's LeCun's bet made concrete. And the result is the one that should make the pixel camp nervous. on predicting what happens next, imagining in latent space beat describing in words by a wide margin, and it did it cheaper. Fewer tokens, better answers.
Cheaper and better, which is precisely the JPA wager, that you don't need to render the future to reason about it, and that rendering it is wasted effort. When they tested the same model with words instead of latent imagination, same data, the latent version won clean.
So the abstract picture in the head carried more than the words could.
And carried the part that matters, the motion, the geometry, without paying to draw every pixel of it. Now, I'll keep us honest. This is a narrow task, and it's a latent reasoner bolted onto an existing model, leaning on a dataset of real future frames to learn from. It's a point for the latent camp, not a knockout.
But put the two side by side. NVIDIA renders the whole future in pixels and gets a system that can drive. This one refuses to render anything and wins a prediction test cheaper.
Which tells you the field genuinely hasn't decided. Both work. They just disagree about what a thought is made of.
So we've got the pixel camp and the latent camp. This next paper is the referee, and its answer is uncomfortable. Use the world model, it says, but distrust it.
Distrust your own simulation.
Right. The setup. A language model doing abstract reasoning. Thinking the problem through in words, plus a world model that can generate a video of what might happen next. The temptation is to bolt them together and let the model reason from the dream.
And the problem is the dream is unreliable.
Their line is great. Generated futures are noisy reasoning traces, not precise oracles. A rollout can look totally plausible and be task wrong. So if you force the model to always simulate, it sometimes swallows a misleading dream and does worse.
They name two failure modes, and both are very human. One, when simulating is optional, the model gets lazy and never bothers, even when imagining would help.
Simulation inertia.
And the other, when you force it to simulate, it gullibly believes whatever it dreamed. So the skill isn't have a world model. It's knowing when to use it and when to ignore it.
So they train that judgment directly. The model decides, should I simulate here? Then it runs the dream, then it judges its own dream. Accept, reject, not sure, and only then answers.
And the training trick is clean. During training only, a teacher gets to peek at the real future and the right answer, and grade those judgment calls, rewarding, you were right to distrust that one. At test time, the real future is gone. It has to make the call blind.
Study with the answer key, then play without it. And it works. It only bothers simulating on about 4 in 10 questions, and it beats both pure word reasoning and always simulate.
Which is the grown-up position in this whole debate. Both camps assume a world model is an asset. This paper says it's a tool that lies, and the intelligence is in the part that knows when it's lying.
Now the contrarian. Everyone so far assumes you need a world model. This paper basically says, for getting a robot to move, maybe you don't. Just scale.
Define the task.
Zero-shot motion tracking. A humanoid copies a stream of human motion it's never seen. A new dance, a roll and stand-up, without retraining for that move. And there's been a stubborn trade-off. Controllers tuned for agile motions break on unfamiliar ones. Controllers that generalize move sloppily.
And their claim is that trade-off isn't fundamental.
Their exact line, it's a symptom of insufficient scale and mismatched training design. So they did the language model thing. 2 billion frames of human motion, they say over 200 times bigger than prior work. And a GPT-style model that just predicts the next pose.
Predict the next pose the way a language model predicts the next word. No learned simulator, no imagined video. A giant next step predictor for a body.
And it works. On a real robot, brand new dances, it improvises in real time. Bigger model, more data, keeps winning.
Here's the tension I want to draw, because it's the heart of the day. OmniDreams says build a rich model of the world and acting falls out. This says skip the world model, scale imitation of motion, and acting falls out anyway. Both get a working robot.
So is the world model even necessary?
For this, copying motion, apparently not. But notice the asterisk they're honest about. They threw out every motion that involves touching objects. No picking things up, no manipulation. And the curve is already flattening. More scale is buying less.
So scaling solved the dance, not the dishes.
Right. Mimic a body in open space, scale handles it. The second that body has to reason about a cup it's holding, that's where you might actually need a model of the world. The contrarian wins the easy half.
The unifiers. Most robots are a reflex. See, then move. This paper says you're skipping the step humans don't skip, thinking about what happens next. So it puts all 3 in one model. Imagine the future, reason in words, output the action.
3 jobs, 1 brain, and the claim is they reinforce each other.
Their line. The next state should comprise both high-level textual intention and low-level physical dynamics. Before it moves, the robot says the next sub-step to itself in words and pictures the scene change in the same head.
And which one actually does the work? We combined three things and it got better is the kind of claim I want the ablation for.
They have it, and it's striking. On long horizon tasks, multi-step with memory, this roughly doubled the best prior approach. And when they removed just the language piece, the subtasks in words, that score collapsed, from the high 50s down into the teens.
So it's the reasoning that cracks the hard tasks, not the imagined future. Removing the world model piece barely dented it. Removing the language reasoning gutted it. That's a clean, honest result, and it cuts against the whole world model is the key framing of the day.
The talking to itself mattered more than the picturing.
For long horizon planning, yes. Which makes sense. Make coffee as a plan, and plans are words before they're pictures. The other nice bit, because the imagination runs on plain video, it can learn a new chore by watching footage, even of a different robot.
No hand-labeled motions.
With the usual asterisk, mostly simulation, one robot, and the boldest, learn from watching anyone claim isn't shown on real human video yet, but that language ablation is the keeper. Reasoning, not rendering, did the heavy lifting.
Now the spooky one. Everyone's trying to build a world model. This paper says one's already in there, by accident.
In where?
In ordinary vision language models. The things that look at a photo and chat about it. We assume they only get flat 2D. There's a dog on a couch, and that real 3D, depth camera angle needs special machinery. This says no. A standard model, trained the normal way, can do depth and 3D about as well as the specialist tools built for it.
With no 3D machinery, how?
That's the claim that got me. No 3D decoder, no special loss. They just fine-tune it to say the answer in plain text. This point is 3 meters away, and on figuring out the camera angle, the untrained model is basically useless. After this simple fine-tune, it jumps near the top of the whole field.
So the geometry was already latent in there, learned implicitly from billions of 2D photos, and the fine-tune just surfaces it.
Native 3D learners, they call it. You learn depth and perspective just by looking at the world your whole life. Nobody handed you a laser rangefinder. They're saying these models did the same.
Which is genuinely strong evidence for the emergent world model idea, that a model of 3D space falls out of predicting 2D images, and you just have to coax it into words. It's the most interesting kind of result, because nobody designed the world model. It grew.
So maybe the holy grail isn't something you build, it's something you find.
That's the seductive version. And the next paper looked at the same idea and concluded the opposite, so before you frame it.
So this is the direct rebuttal, and I love that they landed the same week. Same question, does a sense of 3D space emerge in these models on its own? Their answer, no. You have to put it there.
Make the case.
They take a small model and explicitly train it to understand geometry from video. Guess the depth, guess how the camera moved, guess the real-world scale, all while it watches. And they argue the geometry does not come for free from ordinary training. You have to supervise for it. After that, the 3D awareness shows up inside the model.
So both papers agree the geometry can live in the model. They disagree on how it gets there. The last one says it emerges from plain 2D training and you coax it out. This one says plain training does not give it to you. You have to drill it in on purpose.
Same destination, opposite story about the road.
And it's not just philosophy, there's a real result attached. Their tiny model, after the geometry training, beats models dozens of times bigger at spatial reasoning. How big is this room? Which way did the camera turn? Something you could fit on a phone beating the giants. And the geometry training is all at learning time, so it costs nothing extra to run.
So who's right? Does the world model emerge, or do you have to install it?
My honest read, they're both partly right, and the gap is the whole story. There's clearly some 3D structure latent in a 2D trained model, that's the first paper. But it's faint and tangled, and forcing the geometry in explicitly makes it far sharper. That's this one.
A seed that's there but won't grow without watering.
That I'll sign.
Back to driving, but a different idea. Most self-driving is a trained reflex, but it never models how the world changes in response to what the car does. This paper gives the car a shared vocabulary.
Vocabulary meaning?
Discrete tokens, like words. They turn both the road ahead and the car's own driving moves into the same kind of token. Steering becomes tokens, the future view becomes tokens, all in one shared dictionary.
Why does that help? The usual world models live in a smooth, continuous space.
Continuous is great at blending, weak at clean, what if? Their argument, tokens are reusable, composable units, so you can play out alternatives. If I swerve here, does that token future show a crash?
So discreteness buys you counterfactuals. You can edit one move and read off the consequence. And the action tokenizing is the clever part. They don't just snap each steering value to the nearest bin and lose precision, they spread it across neighbors so the exact value is recoverable.
And one model does all of it. Predict the future given an action and choose the action. World model and driver in one. With a nice tell, a surprise signal that spiked exactly when a counterfactual move would cause a crash.
So it genuinely modeled consequences, not just correlations. The surprise tracks real danger. Now the framing for the day. Everyone's fighting pixels versus latent, continuous versus the rest. This one doesn't pick continuous or pixel. It discretizes everything into tokens, then runs a refine the whole thing edit loop over them.
Discretize, then diffuse.
And the real prize isn't discreteness for its own sake. It's that tokenizing the actions too, not just the pixels, is what lets one model both imagine and drive. The unification, again.
Here's a problem haunting this whole field. These world action models, the ones that imagine the next video and plan the move together, are gorgeous and far too slow. The reference one takes about 8 seconds of compute per move.
And a robot needs roughly half a second, so it's 16 times too slow to actually run. What's the fix?
The obvious one, distillation. Train a fast student to do in one shot what the slow teacher does in many steps. The same trick that made image generators real-time.
And I'm guessing it doesn't just work, or this isn't a paper.
It breaks. Badly. Because the model is doing two things at once, imagining video and planning actions, and those two live in different noise worlds. Apply one compression recipe to both, and the action half basically stops getting a learning signal. Success cratered, from about 9 in 10 tasks to 1 in 4.
So the naive distillation lobotomizes the hands, and the fix is to give each half its own recipe.
Match the compression to each stream's own statistics. Do that and you get the speed. About 20 times faster, fast enough to run on a real robot, while keeping most of the skill.
This one's a nice bridge to the rest of the week, actually, because tomorrow's whole theme is distillation, teaching small, fast students from big, slow teachers. And the lesson here is sharp. Distillation is not one size fits all. The standard image generation playbook silently fails the moment you ask the model to also act.
And the cost of getting it wrong isn't a blurrier picture.
It's a robot that freezes mid-task, which raises the stakes on compress it carefully considerably.
Quick change of scenery, literally. Most type a sentence, get a 3D room tools work from a furniture list. A bedroom with a bed and 2 nightstands. This one works from what the room is for.
So the input is a function, not an object list.
Right. You say a bedroom for a couple where one reads late while the other sleeps early, and it designs the room around that life. Their point. A room isn't a pile of objects, it's a proposal for how a space gets used. A layout can look perfectly plausible and be a terrible place to actually live.
I like that reframing. And the method has a lesson that travels well past interior design. How does it keep the model from just hallucinating a nice-looking room?
It doesn't trust the model to eyeball it. It places furniture, then literally measures with tools. Can you walk past the bed? Does the screen face window glare? And fixes its own mistakes in a loop.
Model proposes, tool checks, model repairs. And here's the result I'd put on the wall. When they took the measuring tools away and let it just think harder, it got worse.
Worse than not iterating at all.
A language model rearranging a room in its head, with no tape measure, talks itself into nonsense. Same lesson we keep hitting. Ungrounded self-iteration drifts. You need something real in the loop checking the work.
And the world model tie?
It's build a world from a spec. If you want to fill a robot simulator with rooms defined by what agents must do in them, not hand-drawn, this is the recipe. Generate the environment from its function and keep a measuring tool honest in the loop.
Last one, and it's the cold sober counterweight to everything we just heard. All day, AI's dreaming worlds. This is a new dataset that asks the unglamorous question, is the ground truth underneath even good enough to catch a dream that's lying?
A dataset paper. Make the case it earns a segment.
Because of what it tests. It's a European driving dataset, sensors that see 4 football fields ahead, and the most complete public map there is, with every traffic light placed in 3D and wired to the lane it controls. And the moment you test today's best methods on it, they stumble.
Which is the point of a good benchmark. Expose what the easy ones were hiding, but tie it to today specifically.
Here's the killer. They test the exact thing the dreamers rely on. Re-rendering a scene from a camera angle the car didn't actually drive, the counterfactual view. And they judge it by something concrete. Can you still read the traffic sign when the virtual camera shifts a couple meters sideways?
And
move the camera off the path the car really drove, and the rendered world stops being trustworthy. The sign's smeared. Which is the whole ballgame for simulation. The entire pitch of a generative world model is, show me the road I didn't drive.
So this is the receipt the dreamers don't want. OmniDreams' best argument was, I can render the path you never took. This paper says, measured strictly on geometry, current methods lose it the moment they leave the real trajectory, and the photo quality scores were hiding it.
Looks real isn't is real, again.
It's the through line of every honest episode we do. A dreamed world is only useful if you can tell when the dream is wrong. And the instruments for that are younger than the dreams.
So pull the day together, one idea, every angle. Did the field decide anything?
No, and that's the honest finding. We watched 4 camps argue. Render the world in pixels. Imagine it in the abstract. Skip the world model and just scale. And it's already in there, you just have to find it. Or no, you have to install it. All 4 had a working result.
Which usually means the truth is it depends. Pixels won the driving simulator, Latent won the cheap prediction, Scale won the dance, and the world model both emerges and has to be trained.
The one thing they all quietly agreed on, though, the reasoning mattered more than the rendering. The unifier's biggest result was the language piece. The referee's whole point was a model that judges its own dream. The world model isn't the prize. Knowing when to trust it is.
What are you watching for?
Whether anyone can tell a good dream from a bad one before it's too late to matter. The last paper said our instruments can't yet. Move the camera, the world smears, and the pretty scores hide it. Fix that, and this whole field grows up.
I'm watching the emergent thread. If a model of the world really does fall out of just predicting images, even faintly, that changes what we think these things are.
A seed, not a blueprint.
This has been Breach Protocol. We crack the black box so you don't have to.
See you next time.